Hey guys, welcome back. I probably should show you what I did. I started the video over again because we were looking at the wrong sensor. Arduino tutorials. I opened the IR sensor and I changed it to sonic sensor because we're going to do sonic sensor this time. And then I saved it as sonic sensor under Sketchbook Arduino tutorials. And I also increased the resolution again. Just because I still wasn't happy with the resolution. I've increased the resolution and the frame rate of what you're seeing on the PC. Okay, let's get into it. Before we get into the sonic sensor, I just want to review something about the IR sensor we did yesterday that I didn't mention. And I thought about it later. Let me bring this up. Okay, on this graph here, when we divided, between LEDs, the amount of voltage we were getting compared to the distance, we did it in a linear fashion. See this curve here? We did it as if a line was going straight down this way. So if you notice, it wasn't an even distance between, even though we divided the, I mean, it was 166 and not 175, which we were dividing by, but it wasn't an even distance in between all three lights, and that's because of this curve. So you see the distance here, and so the voltage translates into the numbers between 0 and 1023. So I think we'll review that, not in this tutorial. And I believe the sonic sensor is actually more linear. But in another tutorial, we'll review how you actually come up with the numbers for this. Or actually how you determine the voltage and the numbers you're getting back from the analog pin on the Arduino. And we could actually map it back to the voltage right within our program if we wanted to. But anyways, enough said. I just wanted to mention that because if you noticed, it wasn't an even distance between all the colors, and that was because this is not a linear line in the graph. It's actually this curved line here. So we have a bigger dip in voltage between, let's say 10 and 30 centimeters. We have a bigger dip in voltage than we do between 50 and let's say 70 centimeters. See, there's not a big dip in voltage here. So there's not going to be a big change in the Arduino sensor reading. So if you notice, I started at like 3 feet, and I'm going down, and that yellow light isn't coming on till around here. But this is the reason for that. Okay, enough of that. Let's get back and let's go to sonic sensors. And which one are we dealing with? I think we have the easy one, which doesn't have a very narrow beam. I have a 4, but we're actually dealing with I have the 1 on the table, so that's the one we're going to use right now. And we need to take a look at the data sheet first. Beam width explanation. This is actually a pretty good one. And let's zoom in on this. And between the different sonic sensors, you notice how we go up in number? The beam actually gets narrower. Each block is a foot here. And each one of these is detecting a pole. They call it a dowel. The equivalent of a pole, and this is the diameter, half an inch, eighth of an inch is really small. And it shows the distance it's able to detect that. We'll look at the 1-inch pole right here. And, the easy one can detect that further, but it's also got a wider beam. And I believe all these guys can detect something, thicker than 3¼ inches, up to 25 feet away, I believe it is. Let me, actually, first let's look at, let me get rid of that. Let's look what it has to say here. Easily enough, the sensor provides very accurate readings from 0 to 255 inches, or 6.45 meters, in 1 inch increments with no dead zone. So we get a lot of information right from this without even looking at the data sheet. But let's look at the data sheet, because we want to see... this isn't much of a data sheet. Oh, it's not the data sheet, sorry. This is an explanation of the beam width. Now let's look at the data sheet. Oh, someone had mentioned before about they asked whether it was DOS on the microcontroller, because they usually do Linux. And basically, you don't have to be concerned with the bootloader on the microcontroller or what it's using for an OS. This is what you need to be concerned with, what we use to program and upload our code. And that, under Arduino download, comes in flavors for Windows, Macs, and Linux. So you just download the Linux versions. Okay, let's go back to this guy. Here we go. This is the data sheet. And let's zoom in on the data sheet. With 2.5 to 5.5 volts. The LV Max Sonar Easy 1, I'm not going to read this to you. 0 to 254 inches. A little over 20 feet. The other ones, I guess, do 25 feet. Come on. Okay, there's a couple of pages here. I hate this. It's not scrolling along. Okay, so what are we concerned with? We want to supply 2.5 to 5.5 volts. We're concerned with these right here. This is our ground. This is plus 5 volts. We have TX and RX. We have analog and pulse width modulation. So this is actually a pretty good sensor for us to work with. Initially, we're going to work with the analog. Like I said, I'm not going to read this to you now. Once again, this is the diameter of the dowels, or just think of it as a pole or a rod, and how far away it can sense, A, B, C, D. So something 11 inches wide, D, you can see over 20 feet. So if you're putting this like in your driveway to sense somebody coming up the driveway, or as a motion detector, it'll see it like 25 feet away, which is a lot further than that last sensor we were doing yesterday. It gives an explanation of benefits. The features and benefits. Please feel free to read those. And here's where I want to go. Okay, so here's the pins. We have ground, return for the DC power supply. Must be ripple and noise free for best operation. So if you had watched the electronics videos when we created our own 5-volt regulator, we had regulated 5-volt power, and we used capacitors to smooth out any ripple or noise from our power supply. So we have 5-volt plus, which is 2.5 volts and 5.5 volts. We'll be putting in 5 volts in there. Capable of 3 milliamps. Okay, that's not the max. It's going to draw more than that, I'm pretty sure. Okay, let's stop jumping around. TX. When BW, leave open or hold low for serial output on the TX port. Okay, so this is for serial output with an RS-232 format. Okay, that's like a serial port on a laptop. You don't really find them too much anymore. You can get a USB to RS-232 converter. I'm a network engineer, so I deal with serial ports all the time. That's how I usually configure most of my equipment, routers and switches and stuff through the CLI, through RS-232. You don't have to worry about this. This is actually an odd interface for a sensor. Usually it has like a TTL, a serial in and out, not an RS-232. RX pin is internally pulled high. The easy one will continually measure range and output if the RX pin is left unconnected or held high. If held low, it will stop ranging. So that RX pin up here, if we put it in this pin right here, if we put it in an Arduino digital pin and pull it low, it'll stop sensing. So we have the ability to turn on and off this sensor by doing that. I don't think I soldered that pin, or I'm not sure if I soldered that pin. We'll check it out. And if I did, actually, let me take a quick look right now. And I did solder the RX pin, so we could actually test that if we want. So I did solder that RX pin. So, okay, so that's the RX pin. Analog. Outputs analog voltage with a signal factor per inch, which is at 5 volts yields 9.8 millivolts per inch. If you notice, I don't think they had a graph on this one showing you the different voltages, because it's a linear, it would be a linear graph. It would be a straight line going down. So it's 9.8 millivolts per inch, and it goes, you know, for 250, we'll call it 250 inches. And so that would be a linear graph. So when we map this one out, we will get an even distance in between all the lights if we keep the same number. PW. This pin outputs a pulse width representation of the range. To calculate distance, use the scale factor of 147 so per inch. So we can actually read we can use a digital pin and read the pulse width modulations, because what happens is with the pulse width modulation, it gives full power on and off very quickly. And I think that's about all we need. I think one more thing I need is the milliamps. The max draw of milliamps. I know the other one I was using was 100 milliamps. Let me see if I can find it. 2 milliamps, 2.5 to 5.5 with a typical current draw. That's very low. I can't imagine it does that when it's sensing. It's extremely low. Okay, and now this one says 3 milliamps for 5 volts and 2 milliamps for 3 volts. Yeah, I guess that's it. Yeah, that's it. Okay, so we have a we're going to be using the analog. For now, I'll actually do a video for the pulse width modulation. I'm not going to do. We'll do serial. We're not going to do RS-232. I hate the way this moves. So we're not going to do the RS-232 on this one, on this particular one. We might do it on another one, because then, and I actually have these. Maybe eventually we will. Okay, I'll cut out a portion of that. I guess eventually we will do the serial, but we'll need a TTL to serial converter, which I have a couple of those. Okay. Let's go back here. See, now this is one of the ones I bought, and when I look at the data sheet for this guy, and I do a milliamps, uh, 50 milliamps peak, and then 100 milliamps with 5 volts. I don't know if you can see that because it's kind of small. The other one does do, so it's 100 milliamps. Anyways, I believe this is going to be fine running off of our Arduino with the 5 volts. So let's go to our code. Okay, now our code is pretty much set up. IR sensor. Well, you know, let's one of the easy ways to change this throughout, and unless you're doing tutorials, you're not going to do this a lot, but we can do a find replace. So we could do IR, and we don't want to ignore case. Sensor, oops. Sensor with sonic sensor. So I prefer to find each one and then replace it, just to make sure of what it's replacing in the code. And that's it, just 2 of them. So basically we read the sonic sensor. Sonic sensor is going to be on pin 5. We're going to use the analog pin. Right now we don't know what these values are going to be. I assume they're probably going to be higher than what our infrared sensor was. So we're just going to leave these values the way they are right now. We already have our serial all set. Let me go through the code a little bit here, just for those of you who didn't have the, for those of you who didn't watch the last video. We have the green LED is in pin 9, digital pin 9. Yellow LED is in digital pin 10. Red LED is in digital pin 11. The buzzer is in digital pin 12. These are capable of pulse width modulation. We haven't done that yet, but they're capable of pulse width modulation. The buzzer is in pin 12, not capable of pulse width modulation, but we don't need that. We have sonic sensor is an analog pin 5, and then sensor value we set to 0 initially. So all these are variables, they're integers. If you go to the reference and you go to data types, you can see, you can click on any of these data types and see what they are. And it'll also give examples. You know, a long is an extremely high number. We don't need that. It takes up more memory on the chip, which is why we just don't use long for everything. Float is for decimals. Anyway, let's get back to this. Okay, so in our setup, the digital pins need to be made either output or input. So here, and once again, the reference will help you with any of this. Pin mode, and it gives you examples. You set the pin mode. So we're setting the pin mode on our digital pins to output, because we want to be able to turn them on and shut them off. And they're going to be output instead of, if it was input, we would be reading the pins. We open up the serial port for our communications so we could see what the sensor value is here. This is our void loop, so this is our void setup. This is our setup function. It doesn't return a value, that's why it's void. This is our void loop. Once again, it doesn't return a value, so that's why it's void. So this runs once, and then this continually runs. So what we do is we read the analog pin 5, which is sonic sensor, and whatever it reads, we store in the sensor value variable, and then we print whatever that value is. Then we have a series of if-else statements down here. Actually, let me just blow this up a little more. We have a series of if-else statements. So if sensor value is less than or equal to 100, do this. Else, if that's what it's equal to, it will just do this. Else, if the sensor value is less than 100 and sensor value is, greater than 100, and sensor value is less than or equal to 275, do this. We reviewed this on the last one, what this is, and this says that both of these need to be true. So it needs to be less than 100, and more than 100, and it needs to be less than or equal to 275. And if both those conditions are true, then it runs this code, this set of code here. And the code is broken up with curly braces. If I look here, boom, see this curly brace to this curly brace? This is the code. Then we have, so if it is, then good, it runs it. If not, it goes else if sensor value is greater than 275, and if we were using the OR, which is the bars, then if either of these were, one could be true and the other one could be false, but then it would run. But we're using the AND. So both of these statements have to be true to run the code. So if it's greater than 275 and less than or equal to 450, run this code. But you notice we're using 450 here. So down here, and it will run this code. And if it's not true, it goes if, else, if sensor value is greater than 450. So that's 451. So if it's 450, this won't be true. That's why both of these can't be true at the same time. And once again, less than or equal to 600, run this code. And greater than 600, and the max we can have on a digital, on an analog pin is 1023. And if it's between 600 and the max, less than or equal to the max, then it will run this. So basically, if this one is true, everything is off. If this one is true, the green light is on. If this one is true, the green and yellow light is the green and yellow lights are on. If this is true, the green, yellow, and red lights are on. If this is true, the green, yellow, red lights are on, and the buzzer signals. So I think you should have been able to get the code from that. I haven't posted the code yet, but you should be able to type it out from that. Okay, I guess we should go over to the video and over to our bench and set this up. And we're not setting it up from scratch. We're going to take apart our existing sensor and we're going to implement this one. And then we'll come back here and take a look at what the readings are, what kind of readings we're getting from the sonic sensor. Okay guys, let's configure our sensor. I did a little prep work, and at the end of this video, if there's space, what I'm going to do is include the soldering of this guy. And I did solder that extra pin. I believe it's the RX pin. And you can actually shut off the sensor with that. So if you're looking to save battery power or something like that, you can actually shut off the sensor. Okay, I actually pre-built this. So let's do it from scratch. Now our setup on our output is the same as our last video, which I hope you watched. But if you didn't watch, let me run you through it. Basically what we have is we have a green wire, a yellow wire, and a red wire hooked into pins 9, 10, and 11. They're pulse width modulation pins, and currently we are not using them as pulse width modulation. We will probably get into that in our next video or the video after that. So they're plugged into 9, 10, and 11, and then each of those digital pins are brought over here. Green is 9, and it goes into, it really doesn't matter what row, and then it's connected to 270, which traverses this trough here, or it bridges the channel in the breadboard. And if you go to the electronics tutorials, you can see a whole breadboard tutorial, which goes to the positive end, which is the longer end of this green LED, and then to the shorter end, in the flat side, if you feel along the LED, the flat side of the LED is the negative side, which goes into this negative rail. And then this negative rail is connected over to the ground on the Arduino. Same thing, now we have pin 10, which is the yellow, 270 ohms resistor, yellow LED, long end positive, short end into the negative, flat side on the round LED. Same for the red. The red wire is pin 11, and that goes over to a 270 ohms resistor, long end positive side, short end negative side. So these are, and I don't have, the buzzer is the 8 in orange, 12. And I don't have him hooked up because, quite frankly, he'd be buzzing right now. Okay, so let's build our sensor. So we have a, it's kind of dark in here right now. We have a ground, which is black, a plus 5 volts, which is red, an RX, which is blue, and an analog, which is orange. So what I'm going to do here on my breadboard, now I could plug it directly into the correct pins on the Arduino, but I want to be able to have a little distance on this guy, move him around. So I'm going to put the negative rail in the negative connection into the negative rail. I'm going to put the positive connection in the positive rail over on the opposite side. Get in there. And then I'm going to put the analog, and the board's actually upside down, so let me do it so I'll do the lower pins. I'm going to put it in row 1, column A, is where I'm putting the analog sensor. The analog pin, sorry. And I'm just going to move this RX out of the way. The only thing we use this RX for is to shut down the sensing. Okay, so he's in there. First thing I'm going to do is I'm going to take the sensor, which is the analog, and I'm going to use this yellow cable for it. I'm going to put it in row 1, column E, which is attached to the same row that this is in. And I'm going to take that and I'm going to put it in analog pin 5. Remember, we have 6 analog pins, 0 through 5. The next thing I'm going to do is I'm going to take this red wire and I'm going to put it in the 5 volts, the 5 volt pin, and then bring it over to our positive rail. And we'll do a close-up of this when we're done, so you guys can get everything in case you're not getting it now. And I'm going to take the ground, and we have 2 grounds over here. I'm going to put it in the second ground, and I bring that ground over to the negative rail. And if you notice, now that I've connected the sensor, all lights are up. And of course we know why, because when we reversed the, or actually you're going to see why momentarily, so. Okay, so we built our sensor. Now I've actually done this. You're about to watch the next bit of code. I had an issue that we needed to resolve, and I actually resolved it, and I want to include that video in this so you can see what I did to resolve this instead of just giving you the command to resolve it. So I'm going to pause this. So don't be confused by seeing the lights right now. So let's stop this. Okay, we went over there, we configured our sensor, and let's see. I didn't have to, I'm using the same Arduino, so, you know, I have the right Arduino selected and I have COM4 selected. Let's open our serial monitor and see what we're getting. We're getting a bunch of ones. Let's see if that changes if I put my hand over it. What I think is happening here, and let me just test by actually moving this. Let's see. Yeah, I think what's happening here is we have the opposite effect. So with the other sensor, the further away you were, the lower the voltage. On this sensor, the further away you are, the higher the voltage. So there's a couple of ways to solve that. We could go in here and reverse all our values. All these values, we could reverse them. Or we can use a map statement just before this. And like I said, I use the map statement all the time. So, and just so for review for you guys, what the map statement does, it allows you to take and remap numbers. So I can take a new variable and I could say map sensor value from 1 to 50 and then remap it 50 to 1 so that I actually change it. Another thing I could do with the map, so I do that sometimes, and that's what we're going to do. That's exactly what we're going to do with this particular issue, to resolve this issue. Another thing you could do is map it to different. Let's say when we start using the pulse width modulated pins, we're going to use a map statement because we can't assign numbers from 0 to 1023 for the pulse width modulation pins. Those are from 0 to 255. So what happens is we'll map 0 to 1023 and we'll map it to 0 to 255. So whatever the numbers are equivalent within that will come out with the pulse width modulation, and it will affect the brightness of our LED. So, but right now what we're going to do is we're going to use this right here, and we're going to remap our sensor information. So let's go back here. Where's our Arduino? What is this? Okay, no, thank you. Don't interrupt me. Okay, so we're going to do, we need another variable to do this. So we have a sensor value, and then we have, actually, I know in processing I can get away with this. I don't know if I can get away with it here. Let me see if I can do this. Sensor, I'm sorry, it's, yeah. Sensor value equals map sensor value, comma, and it's 0, comma, 1023, comma, and we're going to remap it to 1023, comma, 0, semicolon. Okay, so now we've remapped our sensor value and reversed it instead of having to go through all this and changing these values and reversing it. We'd have to have 1023 up here and figure that out. Now we've just reversed the values here. So let me make sure that I didn't make any syntax error mistakes by compiling the code. And if I uploaded it, it would compile it for us. And so now let me upload the code. So I guess I can, well, we'll see what happens. So I've uploaded it. Now let's open our serial monitor. And, okay. It actually worked because I'm looking at all the LEDs. The problem is we need to show this. Cut this. So what happened here is we're showing the sensor value before we remap it. Now we want to show the sensor value after we remap it. So once again, let me upload the code here. And it's actually, whatever I've redone, it's actually recompiling it and uploading it to the board. So now when I open up the sensor value, when I open up the serial port and we see the sensor value, come on, serial monitor, here we go. See, now it's remapped backwards. So now as my hand comes down in front of the sensor, the numbers go up. And as I move away, the numbers go down. But as you can see, we've actually got, we've actually got a lot of distance here. We've got 25 feet we're dealing with. So these numbers are pretty high. Okay, let's stop this and go back to, let's save this, of course. Let's go back to the video camera. It's still. Okay, guys, this is actually another day. I needed to stop for a couple of reasons. But anyways, back to it. Actually, I was doing some experimenting. So that should be 1023, and then this should be 1023, and then let's save it. Okay, so basically, to understand this map value, we're taking whatever the number is in sensor value, and we know it ranges from 0 to 1023, and we're turning it around, and we want it to go from 1023 to 0. So basically, if we're getting a 0 reading from our sensor, we're now going to see it as 1023. So basically, it just reverses whatever the value is. Of course, the value in the middle will be exactly the same. Whatever the value in the middle is. I believe it's close to 512. I don't know whether it's 511 or 512. But that will be the same, because so basically this is translating into this. Now this map command is actually much more powerful, which we'll learn in pulse width modulation. And what we could do with pulse width modulation is we can map this 0 to 1023 to, and we would put 0 to 255, and then it would take the equivalent values and map it. So if it was 1023, it would come out 255. If it was say 900, it might come out 252. I'm not sure exactly what the numbers are, but the map command is a very powerful command. And in the reference guide, it tells you to use another value. I believe it says variable y equals map, and then x, whatever x is. But I've actually found that this command actually works. So that's the map statement, a very powerful tool. Also, because this is another day, the beginning of this video, you see, was also done on another day. And the showing, when I actually showed you, when we put together the sensor a few minutes ago, actually it's probably a few seconds ago, I don't know, and you saw all the lights, I had actually done this already and uploaded it. So you should have seen it as dark. So if you're getting confused, if you're following along, just know this is a little bit out of sequence, that I actually put together the video after I uploaded this to the, I put together the sensor video after uploading this. So I know it seems a little out of sequence, but I'm sure you guys can understand what I'm talking about. Okay, so we've remapped our values, and I'm just going to upload it again, even though I don't have to, because this code is actually on that microcontroller. And of course, everything comes on, and when we look at our serial monitor, you know, we're in the 900s, so we're reversed. We don't see, you know, 111 anymore. But now we have a problem. This sensor detects objects up to 25 feet away. Well, what is 25 feet away? Well, 25 feet away is 0. And now I have this pointed at my ceiling, and I'm getting 980. So when I put my hand over this sensor, you see this value goes up. So basically, we're dealing with around, say, my hand about 3 feet away, 994, to 1012. So we're dealing with a small, very small number. So one of the things we could do is we could work with the map statement. Try different values here. Maybe instead of making it 0 to 1023, we made it, 900 to 1023, and then we did 1023 to 900 on this side, and that would probably work. We could probably put our hand down and get these numbers. But I wouldn't do that in real life, because this sensor is capable of going beyond those ranges. And if you do that, you wind up getting negative numbers and stuff like that. So for the tutorial, I could do that, but because I wouldn't do it in real life, I'm not going to do it here. In real life, this is how I would map the sensor. And then I would actually adjust these values. Now, they're going in the correct order. But for the tutorial, I'm going to adjust these. Let's take a look one more time at our serial monitor. And it's 978. And you see it slowly goes up as my hand goes down. So what I'm going to do is I'm going to say anything less than, let's see, less than 980 is this. Is everything's off. Anything less than 980. So when I load this code, anything less than 980, boom, all those lights should go off. And then less than 980 or equal to. Now greater than 980 is what I'm going to put here. And I think we only went to like 1014 or something like that. So there's not much to work with. We're trying to reduce like a 25-foot sensor to 2 feet here. So we're only grabbing a little bit of it. Let's say 985. The problem is if I do it too close, you're going to see all these lights kind of flickering on and off. Actually, there's a term for that in electronics. It's called bouncing. And when we get to a push button, now you may think, well, we did an infrared sensor and we did a sonic sensor. A push button should be easy. Well, you should actually watch the push button video when I complete it and upload it, because we're going to debounce the push button, and we're also going to do two different styles of the push button. We're going to have the light, or whatever it is, we're going to have it come on while we're pushing it, and then shut off when we let go of it. And then we're going to do another another piece of code that says when we push the button and let it go, the light stays on, and we push the button and let it go again, the light goes off. So you may think a push button is would be very simple compared to what we're doing here, and it is, but it's not so simple as just a digital read to see whether the pin is high or low. Okay. That said, let me do 990. Oh no, sorry, 985 to 990. And is this okay? So 990 to 1000. And anything greater than 1000. Save. Okay, so basically we have our variables for our green LED, which is in pin 9, yellow in 10, red in 11, buzzer in 12. The sonic sensor is in analog 5. There's a digital 5 too, but the variable doesn't determine which one it's in. We're just assigning the number 5 to this variable. When we actually use it, see sonic sensor, we use analog read, so that's where we're telling it that it's in the analog pin 5. And then sensor value, and we're just initializing it to 0. Then we set up and we create our 4 digital pins as outputs. We open our serial connection, and we read our sensor value from sonic sensor, which is pin 5, and then store that in the sensor value variable. Oh, I was messing with some stuff here. Let me actually delete that. And actually, I'll get rid of the delay too. Okay. So then after we remap our sensor value. So when it reads, it's actually going to give us the opposite value. If it's reading 1023, it's going to give us 0. If it's reading 0, it's going to give us 1023. And it's going to reverse all the numbers in between those as well. Then after it's remapped, we print it out to the serial. Now if you remember earlier, we were getting the same thing because we had to move this down. Then we have our conditionals. You know, if this, then do this. If this, do this. If this, do this. And so on and so forth. Okay, I think we're pretty much ready to upload and test this code. So I'm going to upload it. Actually, let me save it. Now let me upload it. And when I upload it, all the lights should go off. And actually, I saw all the lights go off. So let's look at our serial monitor. And we're seeing 978. And of course, if I put my hand there, it immediately goes up. But now we have it. So let's actually move over to... I'm going to pause this, and we're going to move over to the bench. Which is my dining room table. Okay guys, as you can see the light's out, but this is a very, very sensitive sensor. Like I said, this will detect an object 25 feet away. Now the only reason I brought up having it as a car and using it on a, to detect whether something's in your driveway or not, is because I had gotten actually I don't know if it was a message or a post. I prefer the post. If you comment on the videos, that way everybody learns. If you send me a message and I respond to it, and I will, then you're the only one who gets the information, gets your question answered. And whereas if you do it as a comment, everybody gets it. So actually that's the preferred method of communications for me, with questions. Just so everybody gets them answered. I should probably set up a vlog eventually, but that's for another time. Oh, one critical thing. If you remember earlier, I said you could use what we had as a backup sensor. Now, I'm plugging a 9-volt battery right now into this Arduino. Now, if you go look at the specs, it'll say that you can use 9 to 12 volts on this Arduino. That does not mean you can direct... see how sensitive is it? I'm barely coming near the thing. Actually, we'll plug in our... let's plug in orange to our buzzer. Okay. Do not plug the Arduino into your cigarette lighter. Even though it's 12 volts, it's not 12 volts of regulated power. You will blow up your Arduino. And by blow up, I don't mean it's going to explode. By blow up, I mean it will never work again. And even if you change the chip, it won't work. Now, how do I know this? I know this from personal experience. So what you want to do is you either want to create a regulator, like we created under the electronics tutorial. We created a 5-volt regulator. You could use a 5-volt regulator. I recommend a 9-volt regulator for this, but there is something else too. I'm not going to show it in this video. I actually have it up in the Robotics Club, and what it does is it gives you regulated voltage, any voltage you want. It's a variable voltage. What it does is it takes the 12 volts from the car and gives you regulated, I believe it's anywhere from 3 to 12 volts. And you can use that, and I'll show you what that is in the next video. Or you watch the electronics videos and create your own regulator. Okay, now let's test this guy. Of course, when my hand goes anywhere near it, forget it. Now, you're not going to see my hand. I'm taking it, it's out of camera, but it's going up. Remember, this is a 25-foot sensor. Now, also remember that this is linear, so it's an even number for the distances. Now, I don't have it set linear. I was just using guesstimates on the numbers I was using. But right now, I'm approximately, say, 2.5 to 3 feet away, or almost a meter. For those not in, the U.S. drives me crazy. We tried to go to the metric system once. I don't know why we didn't, but okay. So now I come down a little. Now see how that's flickering on and off? That's considered bounce, and we're going to deal with that in working with push buttons. So then I come down some more, and then the yellow light comes on. I come down a little more, and the red light comes on. And my hand's off camera, but it's an even distance between all of these. And actually it works out to probably about 6 inches each one. And by the time my hand's in camera, but we're dealing with the 25-foot sensor here that I'm just doing a lab on. Okay, so basically this is our next sensor. See, look at this. We did a sonic sensor. But like I said, this was a little more difficult because the analog output was opposite to what we were doing with the infrared sensor. And you're going to run into these things. You're going to run into sensors that you have to have a pin high or a pin low. And by high, I mean you have to put it in the plus 5 volts. By low, I mean you have to put it into the ground before it'll sense. Now this one, you actually put into, I believe it's low, and it'll stop sensing. But I did that, and I'm actually getting some weird readings on the Arduino. So, but anyway, now we have the sonic sensor. And it works perfectly fine. And I could adjust those numbers that I put in there so it would work. It would start 25 feet away. And maybe I could have whatever the reading is at 20 feet away, it turns green. and at, you know, maybe 15 or 10 feet away it turns yellow, and maybe at 10 or 5 feet away it turns red, and maybe at a foot away it sounds, you know. And it's a linear, it's a lot easier to figure out because it's a linear pattern on the, it's an even distance, an even amount of voltage for the distance, no matter how far you're away. And you can actually look that up as we did in the data sheet, and to see how much voltage you get per inch. I think it was per inch on there. Let's see. Okay, so that worked great. We changed these numbers here, and I could have actually increased them so that you could see my hand, but and one of the things you could do with these sensors, you could test them and see what numbers you're getting back. Like, let me open this up now, and there is the green light right there. There's the yellow light. There's the red light. And there's the buzzer. So, you know, you can set this however, whatever distance you want. You could have these lights come on. You could have many more lights come on. You could have all kinds of, and once we get to the output, you could have all kinds of output based on this. You could have lights come on, you know, whatever it is you want, you can actually do. And that's one of the things we're trying to do here. Is my goal for the Robotics Club and for these videos is the same for myself as it is for my goal for you guys. And that is, and that includes the ladies, that is to be able to take whatever it is you can imagine and then build it. Okay, anti-gravity machine? No. But what I'm talking about practically, you know, anything you want to build. You want to automate your whole entire household, computerize everything with microcontrollers and a computer and communications, and you want to be able to look at your Android phone from anywhere in the world and see exactly what's going on in your house, or no matter what it is. Write your own video game and a little video game display, because we're actually going to be creating video games and processing. We're also going to do communications. We're also going to do communications in processing as well. And so that's it. This is the code here. The only real thing we changed, we did change these numbers. And actually, let me save that. We did change these numbers only so you could see it in the lab. Otherwise, I would have done maybe 100 to 300, and then 300 to 600, and then 600 to 900, and then 900 to 1023. And those numbers would work for a distance of 25 feet. And as you got closer, I don't have 25 feet distance in my house. So, anyways, once again, once I get the code posted, and I will, I have a website, hdvidi.tv. I'm going to post it up there. I will put links in there. Until then, I hope the code is legible enough for you to type it out on your own. But I will, hopefully I'll get it up there this week. Thank you very much. I look forward to our next tutorial, which is going to be on push buttons. And once again, don't miss it because it's a push button. Have a good weekend, everyone.